Hi everyone, this is an example from lecture 19 on non-Newtonian pipe flow. So in this example I want to derive let me see, where did my mouse go? I want to derive the flow profile for a power law fluid. And I wanted to note that this example is also done out in your book. So example 7.5-1 in your book on page 175 to 176 does this out for you. But in that example, there's a mistake in one of the equations. So what I'm saying here is equation 7.5-8 is missing a factor of n over n plus 1. And since that factor is, anyway, so I just wanted to point that out. That should hopefully come out in our derivation, that difference. Okay, so this example, what we're looking at is pipe flow for a non-Newtonian fluid. In particular, we want to look at a power law fluid. And so I have a cylindrical pipe here. My coordinate system is set up similar to how I did in the previous example. Z is in this direction, and R is in this direction, and theta is around here. I'm calling Z0 the beginning of the pipe, Z equals L the end of the pipe, and I have a dynamic pressure at the beginning and end of the pipe. So you can remember that the dynamic pressure, curly P, is equal to P plus rho GZ. Okay, so that if I take the derivative of P, I get the derivative of dP plus rho G. All right, and to derive pipe flow, I'm going to assume three things. I'm going to assume it's steady, that is, that time derivatives are zero. Axisymmetric, that is, derivatives in the theta direction are zero, so derivatives around the pipe are zero. And unidirectional, meaning that I'm only going to have flow in the z direction, not in the theta direction or in the r direction. So that means v theta and vr are zero. And so I wanted us to recall also briefly, if you remember, we talked about non-Newtonian flow, and we drew these little axes, and I said I had the viscous stress, or the shear stress, versus the shear rate. And I said Newtonian was a straight line, and power law went above or below it, and I wrote this expression tau equals ms to the n. And so what I said was that the shear stress was equal to some constant m times the shear rate to the n. So now we've been a little more sophisticated about shear stresses and shear rates in this part. We've been using viscous stress tensors instead of just simple shear stresses, and we've been using rate of strain tensors instead of simple shear rates. In this case, it's hard to write down an expression like this. So your book writes down an expression for the shear stress, and if I can see, I had just looked at it in your book a second ago. They write down, I don't know where it is, something like that the shear stress is equal to m times 2 gamma to the n, where this gamma, they mean the norm of the viscous stress tensor. And so if that means something to you, you can go read about that. I'm not going to talk about that at length anymore, but you can go read about what they're trying to do here. Maybe that will help you draw some connections. Instead, I'm going to just make some sort of hand-wavy arguments to hopefully justify what's going on here. So I've taken the liberty of writing down our governing equation, and the governing equation here is the Cauchy momentum equation, not the Navier-Stokes equation, because remember, for the Navier-Stokes equation, we had to assume Newtonian fluid and something at a constant density, incompressible. So what we need to do here to solve this problem is to do the same steps that we did when we had the Navier-Stokes equation and use our assumptions to simplify. And then once we have those assumptions to simplify, we can go ahead and solve it. So the first thing we can do is look at these three things. So we say steady, which says the time derivative equals 0. So that means this guy right here will be 0. Axisymmetric, which says that theta derivatives are 0. So here's a theta derivative. So this term will be 0. And unidirectional, which says that v theta and vr are 0. So this guy with the vr in it, that will be 0. That product will be 0. And I have this guy here, which is dvz dz times vz. Well, I know vz isn't 0, but what about the dvz dz? Well, I can come down here and recall, just trying to erase this extra stuff that's not useful yet. If I have the continuity equation, that's going to tell me something about dvz dz. So I can look in table 5.1 in your book, which is on page 111, and I can look up the continuity equation. And the continuity equation, I'm going to assume constant, this is constant density, gives me 1 over r, let's see, the r derivative of RVR plus 1 over r theta derivative of v theta plus dvz dz equals 0. So now if I have something that's unidirectional, v theta is 0 and vr is 0. So that means that guy is 0 and that guy is 0. And both of those go away. And that means then that I'm left with dvz dz equals 0, which I said was fully developed flow. Okay, so that's the fully developed assumption. So that means that guy is 0. All right. So everything on the left-hand side is 0, and now I'm stuck with this stuff on the right-hand side, and that's kind of what I've started to sketch out here. So I've got these derivatives of the viscous stress tensor, tau rz, tau theta z, tau zz, and I wrote out my tau right here just so we could remember what it was. So I have tau rr, tau r theta, tau rz. So, you know, these are, let's see, RZ, theta Z, and ZZ. So these are these guys right here. This is coming from my del dot tau. That's what's coming out here. The grad P gives me that term there. And I don't immediately know how to evaluate these because this comes from the relation for the power law, right? This comes from tau is ms to the n, but I don't know the general expression for that. So this is where I'm going to make some hand-waving arguments. So in the Newtonian fluid, I can write down this guy. I can write down that tau is equal to 2 mu gamma, where if I plug in gamma, I get this guy in terms of the velocity gradients. And so I can write down things for Newtonian fluid for, say, tau rz. And this would be, there's a table in your book for this guy. This is on page 143, table, I'm looking here, 6.5. Okay, and this tells me that tau rz is equal to, where'd it go? There it is, mu dv zdr plus dvr dz. Okay, so I would expect, you know, this is mu and this is my shear rate in some sense, right? Or, you know, some 2 times my shear rate. So if I'm going to have tau is ms to the n, then I'm going to have something like this to the n power, and I'm going to have an m here instead of mu. So the same velocity derivatives that matter for the Newtonian flow also matter for the power law. So tau rz for the power law is also going to be a function only of dvz dr and dvr dz. Okay, and I can look up the other ones as well. So if I look up tau theta z for Newtonian, so I'm going to write that, let's see, I'll put Newtonian. That one is equal to, let's see, theta z is mu dv theta dz plus 1 over r dvz d theta. Okay, so notice this guy has v theta and vz's with respect to theta, and if I look up at my assumptions here, I have v theta is 0, So that guy is going to go away. And then I'm axisymmetric, so derivatives with theta is going to go away. So that guy's going to go away. So tau theta z theta z parallel is going to be a function of those same guys, dv theta dz and dvz d theta. Okay, and let me add a new page here. All right, and I'm going to see the same thing with tau. Which tau is it? Tau zz. So tau zz for Newtonian fluid. Again, looking in the table, gives me 2 mu dvz dz. And so tau zz for a power law fluid is going to be a function of dvz dz only. Okay, so the same derivatives come into play between the Newtonian version and the power law version, the Newtonian version, the power law version, etc. So the same assumptions that cancel out the Newtonian version are going to cancel out the power law version. So tau theta z is only going to depend, I said down here, that's going to depend on these derivatives right here. So this one is going to go away and be 0, not theta, 0. Okay, and tau zz, that only depends on dvz dz, which is right there from fully developed to 0. So that guy is also 0. All right, so lots of things cancel. And let me just rewrite what's going on. So I'm going to have 0 equals this guy plus that guy. So let me write that down. 0 equals minus dp dz plus, and then this one right there, 1 over r d dr, and then I think there's, man, sorry for the scrolling, r tau rz. R tau rz. Okay, so that's simplified. Finally. Took a while. Okay, I took a little bit longer to try and make sure I explained that whole thing. Okay, so now that I have tau rz, I'm going to be able to write what tau rz is in terms of, I want to write down the tau is ms to the n. Okay, and in this case, tau rz, let me just make sure I don't make an algebra error in my notes. Tau rz is equal to m dvz dr to the n. All right, and to justify that, I just want to put down my just a little drawing here. And what I'm saying is that I have, vz, and it's changing in the r direction. So I have vz changing, oops, not zz, vz changing in the r direction. And that is what's giving me my shear rate, right? So vz changing in the r direction, and then I'm taking that to the n power, multiplying by m, and that's giving my shear stress. Okay, hopefully that seems intuitive to you. So I can now just take that guy and plug it in there. So I get 0 equals minus d curly p dz plus 1 over r d dr r multiplied by m, and then dvz dr to the n power with a big brace around it. All right, and now I have everything in terms of p and vz, and I need my boundary conditions, which are the same as the ones for Poiseuille flow, which is vz at r equals 0. That's no slip. And vz has to be bounded, so it can't be infinite. All right. So now we can solve the same thing that we did before. Now it's just math from here on out. Okay? It's math from here on out. So let me do the algebra. Let's do it together. All right, so the first thing I'm going to do is move this to the right-hand side. So I'm going to say d curly p dz is equal to 1 over r ddr of rm dvz dr to the n. Okay, now I said this is a p is a function of z only, and vz is a function of r only, so this must equal a constant. All right, and so if dp dz is a constant, then I can say that dp dz is equal to delta p divided by L. So if I said my slope, the derivative is equal to a constant, I can set it equal to the slope. So that's that first step. And now I'm left with 1 over r, derivative of r, rm dvz dr to the n equals delta dynamic p over L. And so from here, it's a separate and integrate problem. So I move the r over, so I get d of rm dvz dr to the n power equals delta dynamic p over, not r over L, r dr. Integrate both sides. From there I get rm and dvz dr to the n is equal to, and I get delta dynamic p over L, r squared over 2 plus a constant. All right, now I can play the same game I've done before. I'm going to divide by rm, so I get dvz dr to the nth power is equal to delta dynamic p over ml r over 2 plus c over r. Oh, need a new page. Okay, and what do I do from here? Well, I need to take the 1 over nth root of this guy, so I can write dvz dr is equal to, I'm going to make an observation to kind of make our lives easier. So what I'm saying here, right, is that this guy right here, that's m dvz dr to the n, that's tau rz. And so I'm saying tau rz is equal to delta p over L r squared over 2, let's see, r over 2 plus c over r. Okay, that's what I'm saying sort of in between these two lines right there. And I can say, just like I can say about that Vz has to be bounded, I can also say that tau Rz has to be bounded. All right, and that's really convenient right here because I have an r in the denominator, and so when r goes to 0, tau Rz blows up, and so I can say that this constant right there is 0. So I can say that tau Rz is actually going to be equal to delta dynamic p over L r over 2, and that constant is just gone. So that makes this nth root a lot easier here because that guy goes away because I found out that it was 0. And now I can say this is delta dynamic p over m L r over 2 to the 1 over nth power. All right, hope I didn't lose too many of you there, but that's just an easier way. I'm applying this boundary condition early using tau Rz instead of Vz, so I don't have to mess with this 1 over n power in my algebra. That's basically all I'm doing. Now I'm going to separate and integrate again. So I get dVz is equal to, let's see, I'm going to have delta dynamic p over ml r over 2 to the 1 over n power dr, and I'm going to integrate again. All right, so this is the easiest thing I think to do here. This is to pull out the constants and do the r separately. So this side's going to be easy, Vz. I'm going to pull out my constant, which is going to be delta dynamic P over 2ml to the 1 over n. And now I'm going to have the integral of r to the 1 over n dr. Okay, so that's going to give me delta dynamic P over 2ml to the 1 over n. This guy is going to be r to the 1 over n plus 1 divided by 1 over n plus 1. Well, what's 1 over n plus 1? That's 1 over n plus n over n is n plus 1 over n. So I now have delta dynamic P over 2ml to the 1 over n. And then this is r to the n plus 1 over n divided by n plus 1 divided by n. Okay, so this I can pull out to the front, and I get n over n plus 1 delta dynamic P 2ml 1 over n r to the n plus 1 divided by n. Okay, I think I haven't screwed that up yet. Oh, I did screw it up. I forgot plus c. I forgot a plus c out here. I call that one C2. Okay, so I'm done with my integral. Now I need to evaluate my boundary condition. So eval boundary condition number 2, which was the no slip condition. All right, so now to do that, I have Vz at r equals r. That equals 0. And what that's going to give me is n over n plus 1 delta dynamic P over 2ml to the 1 over n, big R to the n plus 1 over n, plus C2. So C2 is going to equal the negative of that guy. So now I can find at the end of the day, I can write what Vz is. N over n plus 1 delta P over 2ml to the 1 over n. And then I've got r to the n plus 1 over n minus big R to the n plus 1 over n. Right? That comes because I just solved for C2 by moving that guy over there. That gives me a negative sign on that. And voila. Alright, let me check with my notes and make sure I haven't screwed it up. I think that's right. So now I can play a couple little games. I'm going to pull r to the n plus 1 over n out like I did before. And I feel like, I feel like I'm missing a negative sign, but let me explain where that comes from. So let me just pull the r out, and then I'll explain my negative sign that I dropped somewhere. N over n plus 1. I can pull out r to the n plus 1 delta dynamic P over 2ml to the 1 over n. I can do that. I'm pulling out an r to the n plus 1 over n. That becomes an n plus 1 here because I have a 1 over n there. And then I have an r over r to the n plus 1 over n minus 1. All right, now I said, remember that this guy in the non-power law, the non-power law version, I had a negative sign. This was flipped around. And that's because I need to be a little bit careful here. When I take the 1 over n power right there, I need to remember that delta dynamic P is less than 0. So I can't take a 1 over n root of that. So what I need to do is I need to actually pull out a minus sign in front of that one and in front of that one. So I need to put a minus sign here and put a minus sign in there, or take an absolute value of that guy. All right, so I'm missing a minus sign out front and an absolute value in all of these little pieces here. So minus sign, absolute value, minus sign, absolute value. Sorry about the error here. Minus sign, absolute value, minus sign, absolute value. Okay, now I get down to here. I'm still missing my minus sign, absolute value, minus sign, absolute value, and one more, minus sign, absolute value. Okay, so now let me pull this minus sign in here, and it'll make it look like our other guy that we had before. So Vz is equal to n over n plus 1, r to the n plus 1, absolute value of dynamic delta P. I don't like that, delta P. Do a better one. Dynamic delta P divided by 2ml to the 1 over n. And now I have 1 minus r over big R to the n plus 1 over n. Right. Now that should look just like equation. Sorry to make it wiggly. That's like equation 7.5-8 in your book, except this should be there and it's not there in your book. So that's the missing part from the book. Okay? So that's how you do that. So now how do you get the friction factor? Friction, oop, that was like the worst F of all time. How do you get the friction factor? Well, you have to calculate tau W over 1/2 rho U squared. And so you're going to need to get tau and you're going to need to get U. And that's your homework question. All right, is to be able to do that. And your book actually has the answer for U. U is in, that's equation 7.5-9. So it's already there. The only thing you have to do left is to get tau W and show what's going on. All right, so that is all I think I have for you. Have a good one.